Okay, so for this review session, what I'll do is first discuss the format of the exam, give you some general helpful hints on the exam, some advice, and then I'll go through an outline of each of the 4 chapters that we will have covered by the time the exam starts. And as we go through those topics, I'll mention some of the key skills that you need to know in relation to these topics and mention some of the sorts of problems that you will need to solve. So if you watch this video before the Thursday night question and answer session on Zoom that I'll be holding, then hopefully you'll have some good questions that you can ask during that time. So the first thing you want to do is look at the sample exam that is posted on Learning Suite, because that is the same format and the same length as the exam that you will have. It will consist of 20 multiple choice questions worth 3 points each, and then there will be 6 or 7 short answer questions that will comprise the remainder of the 40 points. The sample test has a 4-hour time limit on it. Do not let that scare you. That is just designed to give you plenty of time to check your answers. The average amount of time that students take on this first exam is usually an hour and 30 to an hour and 45 minutes. And in fact, because students didn't need those 4 hours to check their time or check their answers or work problems they got stuck on, we're going to shorten it by about a half hour this time to 3.5 hours. So your exam will have a 3-hour and 30-minute time limit, and I don't anticipate that to be a problem for anyone because the exam is designed to be completed within an hour and a half. And so that will give you plenty of time if you get stuck on an individual problem or if you like to check your answers. Now, of course, with organic chemistry, there's usually a range of times that it takes people to complete the exam. Some people will finish in less than an hour. Other people will take 3 hours or so. So just make sure you budget the appropriate amount of time based on generally how long it takes you to take an exam. If you're one that usually takes a little longer than the average amount of time, then you should make sure you've got 2 to 3 hours available to take the exam. You don't want to get kicked out of the testing center before you finish. Please remember that on Mondays, the testing center closes at 7. They give out their last exams at 6. So don't try to go into the testing center after 6. They won't let you in. So molecular models are encouraged. We're going to start talking about those in class on Wednesday and also on Friday. So you should get a set of molecular models, and you'll be allowed to take those into the testing center. However, unfortunately, in the past, there have been some students who have smuggled cheat sheets in with their molecular models. So to eliminate that, the testing center requires you to use airport security style measures for your molecular models, meaning you have to place them in a clear plastic bag so that they can look and make sure that there's no papers or cheat sheets hidden inside with your molecular models. So if you bring them in with a clear plastic bag, you also have to have them on your desk the whole time. If you have them in a bag underneath your desk and you reach and you pull them out at some point during the exam, then you could get flagged for cheating by the proctor. So make sure you bring them in a clear plastic bag. Make sure you have them on your desk the entire time that you are in the testing center. And your molecular model set does not have to be fancy. If you can make a 6-membered ring with 3 substituents coming off of that ring, that's going to be a large enough model set to be able to work the problems that you'll see on this particular exam. So in addition to the sample exam, the best preparation for this exam is working the homework problems. You'll see many of the same types of problems as the homework problems. And I'd like you to pay particular attention to the challenge problems at the end of each chapter. So the most difficult problems on the exam are designed to be of a comparable difficulty to the challenge problems at the end of each chapter. So the golden question in this class is, what do I need to do to get an A? And so whenever students ask me that question, my response is work and solve the challenge problems. So students who are proficient at solving challenge problems are usually the types of students who will earn full credit on those most difficult problems that you'll encounter on the exam. And those students tend to end up in the A range. So please pay particular attention to the challenge problems. And if you want additional practice beyond the assigned homework problems, you're welcome to work the challenge problems that were not assigned. Those are great problems as well. So these are the things you can do to prepare for the exam. One final bit of advice that I will give you is take the exam early in the time frame that it's available. Don't be afraid to take it on Friday. So the natural tendency of students is to procrastinate. And I like to track the average scores of students that take the test on each day. So at the end of each day in the testing center, I log in and I check what the average is at that point. And the average always goes down over time, meaning that the students who take the exam on the first day that it is available have the highest average, and then the students who take the exam on the last day that it's available have the lowest average. Now, I'm not suggesting that you take it on Friday if you're not prepared to take the exam. You obviously need to be prepared regardless of which day you take it in order to get a good score. But the students who are organized in their preparation and are prepared to take the exam on Friday should take it then and shouldn't wait, because in the past, there's plenty of students who've done very, very well taking the exam on the first day that it's available. Even though we're not finishing this unit until Friday, if you're very, very well prepared with everything that we've learned up until Friday's lecture, and then you just take a little bit of time after class on Friday to solidify the concepts we've learned in class, there's nothing stopping you from going into the testing center late in the afternoon or early in the evening on Friday to take the exam, because the students who are well prepared and who do that always end up scoring well. So don't procrastinate, take it early in the period, then you can enjoy your socially distanced weekend and avoid getting COVID, but not have the exam looming over you for the weekend. So with that, let's go into an outline of the topics that we have learned or will learn in this unit of the class and discuss some of the key skills that you will need to be proficient in related to each of these topics. So I've gotten a little bit of a head start, and I've written some of them on the board already. Chapter 1 was entitled Structure and Bonding. This is a review of, largely a review of things you learned in general chemistry. We started out with Lewis structures. So you need to be able to draw valid Lewis structures. We built on that by then discussing resonance structures. And as I've said before, resonance structures is an incredibly important topic, because students who understand resonance structures are able to draw resonance structures correctly, are able to use curved arrows to show the relationships between resonance structures, usually do very well when we get into reactions in chapter 7. So it's very, very important to be able to draw resonance structures, to be able to use curved arrows to show relationships between resonance structures. It's also important to be able to look at different resonance structures and identify which one is the major contributor in cases where there is a major contributor, versus cases where there are equal contributors. Okay? So a very, very critical topic. After resonance structures, we had a discussion of two related topics, shape versus geometry, which are often used interchangeably, but in our book and in the class, we use shape to refer to a molecule, and we use geometry to refer to atoms. So when we were determining geometry at atoms, we looked at the number of groups. We included lone pairs. And so that's directly related to the hybridization and the number of groups. When we determine the shape of a molecule, we first determine the geometry, but then we remove those lone pairs. So we end up with water being bent, even though it has a tetrahedral oxygen, for example. So it's important to know the difference between these two terms. We learned how to draw organic compounds in different ways. The book refers to condensed structures and skeletal structures. You should be familiar with both because you'll see both types of structures on exams, much like you have in the homework. And so it's important for you to be able to interpret these structures as well as draw them yourself because you will have to draw some structures on the short answer portion of the exam. We then went into a discussion of bonding, and there are two theories of bonding that we discuss, our valence bond theory. And valence bond theory, I'll also write up here, encompasses hybridization. Okay, we spent some time talking about hybridization. There were some very helpful figures that were not in the book that I showed you in class. And all the figures I show you in class are available on Learning Suite, so you can take a look at those figures. So you need to understand the hybridization process and the valence bond theory, which you've learned previously. And then we had molecular orbital theory, which most of you have probably learned, but maybe to varying degrees, depending on the general chemistry class you took. At this point in the class, we just need to know the basics related to molecular orbital theory, the basic concepts, the fact that we generate molecular orbitals by combining atomic orbitals. The way we combine them is we either add or subtract them. Lower energy orbital, the lowest energy orbital usually has 0 nodes. And then when we end up with higher energy anti-bonding molecular orbitals, they end up having 1 or more nodes. In the case of hydrogen, we just have a bonding molecular orbital with 0 nodes and an anti-bonding molecular orbital with 1 node. Okay, so just that basic discussion of molecular orbital theory that we went through in class is all you need to know for now. And we'll build on that at later points, largely in Chem 352. All right, so that's as far as I'd gotten in writing on the board before we started. So let's come over here and continue with our Chapter 1 topics. We discussed the relationship between bond length and bond strength. Okay. We learned that shorter bonds are stronger bonds. We discussed why certain carbon-hydrogen bonds are stronger or shorter than others. So that's something you should understand and be able to explain. And then we concluded the chapter with a discussion of electronegativity and bond polarity. Okay. So we learned that any bond in organic molecules other than carbon-carbon and carbon-hydrogen bonds would be polar due to electronegativity differences. And then the greater the difference, the more polar the bond is. And then the final aspect of this that's important is to distinguish between polar bonds and polar molecules. Okay. We said that there are some molecules that have polar bonds, but the molecules themselves are not polar because those dipoles cancel each other out. And we gave examples of that. There's a figure in the book that shows that. All right, so those are the key topics from chapter 1. So let's go into chapter 2 now. So chapter 2, acids and bases. Another topic that you learned in general chemistry, but we learned it a little bit differently in organic chemistry, focusing more on qualitative issues as opposed to calculations or quantitative issues. So we started with our definitions. We've got the Bronsted-Lowry definition of acids and bases. That's the one we spent most of the time on in the chapter. But we also talked about Lewis acids and bases. So you should be familiar with both types of both definitions and look at structures and be able to decide if those compounds are Bronsted-Lowry acids and bases or if they are Lewis acids and bases. Okay. Then we talked about acid-base reactions, which are equilibrium reactions. Okay. So you should be able to identify the components of an acid-base equilibrium. We have our acid and our base on the left side of the equation. We have our conjugate acid and our conjugate base on the right side of the equation. So being able to identify the components of the reaction, and then also being able to determine if the reaction favors the products or favors the reactants. Remember, we said that these equilibria will favor the formation of weaker acids and bases. So the conjugate acid and the conjugate base should be weaker than the original acid and base in order for the reaction to be favorable. Okay? We talked about acid strength. We spent a lot of time talking about acid strength. We began by mentioning two parameters that we could use to measure acid strength. There's Ka, the equilibrium constant of an acid-base reaction. But since most of our organic acids are weak acids and Ka is usually a very, very small number, much smaller than 1, it's more convenient for us in organic chemistry to use pKa. Okay? So it's important to be able to compare pKa numbers and determine which acid is stronger and which acid is weaker. Okay? In conjunction with pKa, we learned how to read pKa tables. So pKa tables have lists of acids and their conjugate bases. We're not worried about memorizing numbers in pKa tables. Please do not spend any time memorizing numbers in pKa tables. That will be time wasted that would be better spent studying other concepts. What we're interested in is you being able to look at a pKa table and interpret the information in it. Namely that as you go down a column of acids, you're going to, the acid strength is going to decrease. So these tables are always organized with the strongest acids on top. And then you have a column of the corresponding conjugate bases. And the base strength is going to increase as you go down. There's that inverse relationship in stability between acids and their conjugate bases. And so looking at using a pKa table and determining whether or not a given acid-base reaction will be favorable is a skill that you would need to know in regards to pKa tables. And we had an iClicker question on that topic. So if you go back and review that iClicker question, that gives you an idea of the sorts of things you would need to know related to pKa tables. But please do not waste your time memorizing numbers in pKa tables. That's just not going to be important. Then we talked about factors determining acid strength. Determining acid strength. So this was a very important topic in this chapter. We had 4 factors, and we apply those factors to compare relative acidities or relative basicities. And then we can rank compounds in order of their acid strength, either from strongest to weakest, weakest to strongest. We can select the strongest acid. We can select the strongest base, rank bases in order of strongest to weakest or weakest to strongest. These are the sorts of problems that you would need to be able to solve related to this topic. And there's plenty of homework problems on this subject, so I encourage you to practice them. So the 4 factors, we had element effects, and there's 2 versions of the element effects. If we're going across the periodic table, we look at the electronegativity of the atoms. That's the property that makes the biggest impact on acidity going across the periodic table. As we go down the periodic table, it is the size. I should remind you that these factors are applied to the structures of the conjugate bases because we said that any structural feature that stabilizes a conjugate base, makes that species lower in energy, is going to increase the acidity. It's going to cause more of that stable conjugate base to be formed at equilibrium. So we're always looking at how these effects apply to the structures of the conjugate bases. And that helps us determine which acid is stronger. So element effects, 2 different properties to consider: electronegativity across the periodic table, size as we go down the periodic table. Okay, then we have inductive effects. So inductive effects occur when we have electronegative heteroatoms elsewhere in the molecule, ones that are not bonded to our acidic hydrogen. And remember, we said that inductive effects are the weakest of our 4 effects. Okay? That all 3 of these others can have very, very strong, very dramatic impacts on acid strength, but inductive effects have a more modest effect on relative acid strength. Okay. Then we had resonance effects. Okay, these can be very strong. If we have resonance stabilization of a conjugate base, then that makes the resulting acid quite strong. And then we had, as our 4th one, hybridization effects. Okay. And so this applies when it is a hydrogen attached to a carbon that is our acidic hydrogen. And we learned that the greater percent S character of the carbon makes that carbon more acidic. And you should not only understand how to apply these effects, you should also be able to explain them, explain why they lead to stronger acids. We have a great table in this chapter that summarizes these effects. And as I mentioned in class, you don't want to simply memorize the information in the table. Rather, if you can look at the table and you can explain the reasons for each of the effects that are listed in the table, then you know that you have a very good understanding of that topic. Okay? And then the last thing that we learned in chapter 2 was the acid-base chemistry of aspirin. We talked about how the stomach is acidic, the intestines are basic. This leads to the acid form of aspirin dominating in the stomach and the conjugate base dominating in the intestines. And that affects in which part of the digestive tract aspirin is absorbed into the bloodstream. Okay, so this is our first example of a molecule that we learned about that illustrates the principles we're learning. And we had many more molecules that we learned about in chapter 3 that we'll go over as we outline that chapter. Okay? All right, so we'll go ahead and erase the board and we will outline chapters 3 and 4 once we have space to write on the board. Unfortunately, they don't have the long erasers in this room, so it takes a little longer to erase the board. All right. So chapter 3, entitled Intro to Organic Molecules and Functional Groups. FG is our abbreviation for functional group. So we started out with the definition of functional groups. These are the atoms or groups of atoms that are responsible for the characteristic properties of organic compounds. And the book mentioned 4 classes of compounds and their functional groups. We have hydrocarbons, where our only functional groups are pi bonds, double bonds, and triple bonds. And some of our hydrocarbons have no functional groups, the ones that we're learning about now in chapter 4. Then we had compounds containing carbon Z sigma bonds. Remember, Z refers to any atom that is not carbon or hydrogen. So in this class, it's going to be oxygen, nitrogen, halogen, sulfur, or phosphorus. And these bonds are polar. And so the characteristic feature that each of these bonds imparts is they give us an electrophilic carbon atom and a nucleophilic or Lewis basic heteroatom that has one or more lone pairs on it. Okay? And that's largely responsible for the chemistry imparted by those functional groups. Then we had compounds with a carbon-oxygen double bond, also known as a carbonyl group. Like the compounds with the carbon Z sigma bonds, in this category we also have an electrophilic carbon, a nucleophilic or Lewis basic oxygen, but we have the additional feature of a pi bond that is more easily broken than a sigma bond. So when we study the chemistry of these compounds, mostly in Chem 352, all of those 3 features will be important. For now, we just need to be able to identify these. And you had these tables in the book that showed names of these types of compounds. And I told you that you should memorize those names. You should be familiar with those names. They are the vocabulary of organic chemistry. We're probably not going to test you directly on those names. We're not going to ask you which of the following compounds is an alcohol, for example. But we are going to use those words. You'll see the words alcohol or amine or alkyl halide. These are words you'll see in homework problems on tests, and you'll need to be able to know what those words are, what they mean. And you might need to use those words as you answer questions, as you answer short answer questions. You might need to use those words. So these words are part of the vocabulary of organic chemistry. To speak the language, to be able to write the language on exams, you need to be proficient with these terms and know what they mean. Okay, and then we had a fourth category, compounds with phosphorus-oxygen bonds. This was a smaller category. We had the phosphoester and the phosphodiesters and so forth, ATP and related sorts of compounds that are important in biochemistry. Okay, so being familiar with the different functional groups, knowing the names of the compounds that contain those functional groups is what we need from this section of chapter 3. Then we had our intermolecular or non-covalent forces. Okay. Your book refers to them as intermolecular forces. I told you that you can have these forces between two different functional groups in the same molecule, so a better name is non-covalent forces. But these are non-bond. These are not bonds like covalent bonds. These are weaker than covalent bonds, but they are forces that attract molecules or different functional groups within the same molecule together. And this again is review from general chemistry. We had three types that we went over. We have the van der Waals forces, the weakest forces, the only ones that we have in nonpolar compounds. But we did talk about molecules or organisms where van der Waals forces are significant. Remember, we mentioned geckos. Van der Waals forces are responsible for the stickiness of geckos' toes. And van der Waals forces also explain the difference between long-acting and short-acting asthma drugs. We went over that example in class. So, in case you're wondering, any molecule that we talk about in class, regardless of whether or not it is in the textbook, is fair game for an exam. Okay? Everything we talk about in class is important. So we do our very, very best to avoid talking about subjects that you will not be tested on. So the asthma drugs are not mentioned in the textbook, but with the explanation that we went over in class, with the figures that we showed you that you can look at on Learning Suite, you should be able to explain the difference between those two asthma drugs, and explain why one is long-acting and gives chronic relief, one is fast-acting and gives immediate relief. You should be able to explain that in terms of the specific intermolecular forces that are available. And in this case, it is van der Waals. So if you look on the sample exam, you will see a problem where we asked you to do that. I believe it was vancomycin that we asked you to discuss on that sample exam. Okay, so our next type of non-covalent interaction, dipole-dipole forces between two molecules. Oh, I forgot something. Sorry. Let me erase that. There's one more concept under van der Waals forces that's important, and that's polarizability. So we defined polarizability, the ability of the electron cloud of an atom to respond to external stimuli. And we talked about how increased polarizability leads to stronger van der Waals forces. So that's an important concept to note. It does play a role in boiling points, as we'll discuss in a few moments. Okay? All right, so now we'll move on to dipole-dipole interactions. Attractive forces between two molecules that have permanent dipoles in them. And then we spent more time talking about a subset of dipole-dipole interactions, the strongest dipole-dipole interactions, which are hydrogen bonds. Okay. Remember that even though these are the strongest of our intermolecular or non-covalent forces, they're still much weaker than covalent bonds. An individual hydrogen bond is usually worth about 5 or 6 kilocalories per mole, whereas a covalent bond is usually worth about 100 kilocalories per mole. And in the context of hydrogen bonding, we talked about one of my favorite molecules, vancomycin, because its mode of action, as well as the way that bacteria resist it, is directly related to hydrogen bonding. So please make sure you review those figures, and you can go back and rewatch the section of the lecture, since all the lectures are recorded, describing how hydrogen bonding plays a role in both vancomycin's mode of action and in how bacteria are able to resist it. Okay? All right. So the second half of this chapter, we focused on how these different types of intermolecular forces impact the physical properties of compounds. One of those was boiling point. Okay. So with boiling points, you would need to be able to place compounds, a list of compounds in order of increasing or decreasing boiling point. You might be given a list of compounds and asked to select the one with the highest boiling point or the lowest boiling point. So these are some skills that you would need related to boiling points. And then related to that was melting points. And we said that the trends of melting points mirror those of boiling points, with the exception of when there is symmetry present. But please remember to only look at symmetry with melting points. It does not impact boiling points. Okay? And then our other physical property that we talked about was solubility. So we have our solubility rule, the same one you learned in general chemistry. Like dissolves like. And then we have our rule for predicting water solubility, where we said you have to have less than or equal to 5 carbon atoms per one functional group that can engage in hydrogen bonding to water. Okay. Now it's important to distinguish between molecules that are capable of hydrogen bonding to each other, to another molecule of itself, that impacts boiling point, and molecules that are capable of hydrogen bonding to water. There are compounds that can hydrogen bond to water that cannot hydrogen bond to another molecule of itself. And so those compounds would have low boiling points, but they would have water solubility. Okay? So regardless of whether or not a compound can hydrogen bond to another molecule of itself, if it can form a hydrogen bond to water, then it will have water solubility. And I forgot to write the 5 here, sorry. That should be less than or equal to 5 carbon atoms per each hydrogen bonding functional group. Okay? And then we spent some time talking about various molecules and how their solubility properties have influenced their use or their functions. We talked about MTBE, which was water soluble and leached out of the gasoline tanks. We talked about PCBs, insoluble, persistent in the environment. We talked about vitamin A. We talked about vitamin C, not water soluble versus water soluble. different issues at play in those cases. So you should understand for each of these compounds how the structure of the compound influences its properties and its function or any environmental problems that come from them. So all of these molecules are fair game in an exam format, so you should be able to explain them the way that we did in class. We talked about how soap works. We talked about micelles. That's a vocabulary word associated with soap, that soap molecules form micelles. We explained how that the intermolecular forces that are involved that enable the soap molecules to dissolve greasy compounds. And then we talked about phospholipids as well. Phospholipids are similar but not identical to soaps. These are both amphiphilic molecules. One forms micelles, the other forms lipid bilayers. Okay? So again, the structure determines the function in those cases. Then we had a couple molecules that were not in the book that are very important and interesting. We learned about ionophores, organic compounds that complex cations. They use ion dipole forces, right? That's a fourth type of force. We didn't list it over here with our intermolecular forces, but ion dipole forces are another type of intermolecular force. And we use monensin, an antibiotic, as an example of a compound that is an ionophore. So you should be able to explain how the structure of monensin enables it to coordinate cations and how it is able to carry those cations across cell membranes. And then we closed with amphotericin B, the antifungal compound, which doesn't carry cations across cell membranes directly, but instead forms an artificial pore or channel in a cell membrane that allows those cations to flow in and out. So you should be able to explain that, again, with particular reference to the types of intermolecular forces that are involved. Okay. So that is our outline of Chapter 3. So let's outline Chapter 4, alkenes. We're still in this chapter, so some of the things I'll discuss we haven't discussed in class yet, but I'll list the key topics and I'll mention some of the key skills that you'll need to be able to solve in regards to those topics. So we talked a little bit about isomers at the beginning of this alkene chapter. So there are problems where you might have to determine the number of isomers of a specific formula. There are homework questions that will prepare you for this. There are questions on the sample exam, both multiple choice and short answer, that also involve this concept. So they won't be any more challenging than the ones that you see in the homework and on the test. We're not going to ask you to draw all the isomers of decane, for example. That would take way too much time. Okay, and then we have some vocabulary that you need to be proficient with. We learned about the degrees of carbons: primary, secondary, tertiary, quaternary. We learned some words: methyl, methylene, methine. Okay. These are important terms that you should recognize, that you might need to use in some context. We learned how to name alkyl groups. Okay. And remember, we only went up to 4 carbons. We didn't name any alkyl groups longer than 4 carbons. So that's as far as you need to go, naming alkyl groups of 4 carbons. And if you understand where the names come from, the tert, the iso, the sec, and so forth, it doesn't involve as much memorization. Then we have my favorite topic, being sarcastic, of course, IUPAC nomenclature. So, how are we going to test IUPAC nomenclature on the exam? There's a couple ways. We might give you structures of compounds and ask you to write the names. Okay. We could do it in reverse. We could give you names and ask you to draw the structures. Okay. And if you're doing the homework and if you're looking at the sample exam, then you'll see examples of both of those types of questions. There's a third way that IUPAC nomenclature will be tested, and that is indirectly. There will be questions where we'll just give the name of a compound in the question, and in order to get the question correct, you need to know what the structure of that name. Okay, so sometimes we'll draw structures for you. Other times we'll give you the name, and you have to know what structure that name represents. So you'll see indirect testing of nomenclature, and if you look on the sample test, you'll see examples of how we've done that. Okay. And this will apply IUPAC nomenclature to both acyclic alkenes and cycloalkenes. Okay. Then tomorrow in class on Wednesday, we're going to start learning about conformations or three-dimensional orientations of molecules. And we'll start out with ethane. We'll rotate about the carbon-carbon bond of ethane, and we'll look at the different shapes that result. And there's some vocabulary associated with this. We're going to look at Newman projections, and you'll need to be proficient in looking at Newman projections. We're going to learn some terms, staggered and eclipsed. These are important terms to understand. We'll learn about dihedral angles, so you'll need to know what a dihedral angle is. We'll talk about strain. Strain is a structural feature that increases the energy or destabilizes a compound. Torsional strain relates to ethane, and we'll learn about that. Then we'll discuss butane. We'll introduce a couple of different concepts with butane. We'll introduce the terms anti and gauche. Okay. Anti and gauche are two different types of staggered conformations. And then we'll also discuss a concept that comes out of anti versus gauche, and that is steric strain, a different type of strain or structural feature that elevates the energy of a compound. Okay, to finish up our Chapter 4 outline, let's come over here. The conclusion of Chapter 4 is going to be cycloalkanes, looking at the conformations of these compounds, comparing them or contrasting them to acyclic alkanes. The biggest difference is that with cycloalkanes, we have restricted rotation. We cannot rotate fully about the carbon-carbon bond of the carbon-carbon bonds of cycloalkenes. Okay? There's a new term, a new type of strain that we'll introduce with cycloalkenes. That is angle strain. So that's an important term to recognize. And we'll talk briefly about 3 to 5 membered rings, cyclopropanes, cyclobutanes, cyclopentanes. But we'll spend most of this section of Chapter 4 talking about our most important cycloalkane, which is cyclohexane. Okay? The most stable conformations of cyclohexane are the chair conformations, so we're going to learn about chairs. There's some vocabulary that goes along with chair conformations. Axial, equatorial. So these are vocabulary words that you should learn. There's a process called ring flipping. You should understand conceptually the ring flipping process. We'll go over that in class on Friday. Okay. We'll talk about monosubstituted cyclohexanes, or cyclohexanes with one substituent coming off of the ring. And we'll introduce a couple concepts in conjunction with this. 1,3 diaxial interactions. Okay. And then we'll talk about A values. All right. A values are not specifically mentioned in the book, but we'll go over them on Friday. And we'll have to use this equation. We'll just use it conceptually, but the delta G naught equals negative RT ln K equation that you learn in general chemistry allows us to relate equilibrium ratios of chair conformations to differences in energy between those conformations. Okay? Just a couple more things that we'll learn on Friday related to cyclohexanes. We'll talk about di-substituted cyclohexanes, okay, where we have two substituents coming off, and that's going to introduce a concept, stereoisomers. Okay, when we have two or more groups on a ring, we can have a type of isomer known as a stereoisomer. We'll learn about that on Friday. The two terms related to stereoisomers are cis and trans. And we're going to learn how to determine which is more stable of a given type of disubstituted cyclohexane, if the cis versus the trans is more stable. And then the last thing we're going to learn is fused rings. This is where we have two or more six-membered rings fused together. And what happens in that case, cholesterol is an example of a compound that has fused rings. And much like we did with vancomycin and the asthma drugs and monensin, we're going to discuss how the structure of cholesterol enables its function in the body, which is to provide rigidity to cell membranes. Okay? So you should be able to explain that as well. All right, so that is the outline of the chapters in this section. So make sure you go through these topics. Make sure that you are proficient in the skills and the problem solving that we've discussed, and you should do well on the exam.